Good morning. Welcome to Freeslate's webinar on automated solutions to accelerate drug development. My name is Justin Fisher, and I'm the Senior Product Manager here at Freeslate, and I have the honor of being your host for today. Today you will hear a presentation on improving the solubility of your API and new technology developments around automating solvent drop grinding to generate co-crystals. We're pleased to have Poo Sun from Freestate joining us today. We will conclude today's webinar with a brief question and answer session. Before we begin, let me invite you to submit questions using the chat window on the lower left-hand side of your console. Any questions that we do not get to will be answered privately in a follow-up email, so please feel free to submit questions throughout the presentation, and they will be addressed. Our speaker today is Dr. Poo Sun. Dr. Sun received his bachelor's degree in chemistry from Hanover College and his Ph.D. degree in organic chemistry from Penn State University under the tutelage of Professor Stephen Weinreb. His graduate research was focused on the synthesis of natural products. He is currently a senior staff scientist at Freeslate, where he manages our small molecule services group in the area of high throughput reaction and pre-formulation screening. His group currently engages collaboratively with major pharmaceutical and biotechnology companies and provides high-throughput screening services that include optimization of organic transformations, polymorph, chiral resolution, and solubility screening. The title of Poo's presentation today is New Technology Development, High-Throughput Solvent Drop Grinding Screening to Generate Co-Crystals. And with that, I will hand you over to Poo.
Thank you, Justin. So here's our overview of my talk. So I will give a quick introduction of solid form and polymorph studies, and now I'll follow up with pharmaceutical co-crystals, which is how we start this particular study or new technology development. I will try to emphasize why there's a need for high throughput research, and I will touch upon how traditionally solid grinding and solid drop grinding technique work. A bulk of the study is this test case where there's a diacid and dipyridine compound that is known to form co-crystals, and there's a comparison between manual approach and the way we do automated high throughput approach that using solvent drop grinding as the technique. And within that, we're going to show you, how we do it operationally, and how our test went through operationally, and also the result from XRD, and see how well that turned out. And then I'll give a summary. So if we just go pretty quick general overview of solid form, so then we have amorphous and crystalline form, and you have either one or more than one forms, and that's more is a polymorphism of a certain compound. And within that, and we can have either a single component that is have crystalline one or more forms, or that you have dual or multiple component, and it could be solvates, hydrates, salts, or co-crystals. And within salt and co-crystal, there's a possibility of forming additional solvates or hydrates. So if you think about how we do a typical approach to a polymorphism study, and the first thing people always can think about is it possible to generate a crystalline form, one or two, multiple form by itself? And if that doesn't work, or there's other studies within the study, you always see something else anyway. It forms dual multi-components. Just like solvates or hydrates. And it depends on the compounds, if they're ionizable or not, you can split into salt or co-crystal formations. If it's ionizable, it can be salt, and the salt can form solvates or hydrates in addition to salts itself. Or if it is weakly or non-ionizable compound, then there's a possibility to form co-crystals, and co-crystal can also form additional solvates and hydrates. So traditionally, forming salt, modification of API, if the API is ionizable to form salt, is a very common approach to solve this and finding the crystalline form. You can get it by itself, just like what we said, and or solvates or salts. But pharmaceutical co-crystals is an emerging and alternative. It's new, definitely new compared to salt formations. And the crystallization is through hydrogen bonding or other non-covalent intermolecular interactions. And it does give you additional options in terms of crystal engineering. And API that form co-crystals have shown to improve solubilities, bioavailabilities, and stabilities. So in this slide, I'm going to show you there might be a need for a high throughput approach. So imagining not all APIs are ionizable structures; they don't have acid or base moieties on it. But virtually all API are capable of forming co-crystals, at least potentially forming co-crystals. And a different technique within forming co-crystals actually might yield different co-crystal formations. And what that means is some co-crystal can only, at least through study so far, and you do form different co-crystal depends on the technique you use. I'm gonna talk briefly about what are the techniques out there. And also, this is just to demonstrate what I said earlier. There's a possibility, the co-crystal has a possibility to form hydrates, solvates as well. So in this particular study, you can see through solvent drop grinding, the compound can form co-crystal by itself or two hydrates and 7 solvates. But if you see, this is a survey done in 2008. Very little has been done in terms of structures discovered and published compared to, other better known structures. So if you take a look at our traditional approach to co-crystallization formation, so there's a solvent-based approach, and there's a slurry solvent evaporation, just like salt forming possibilities as well. And then there's a sonic blending, and there's a solid grinding, solvent drop grinding technique, and there's a hot melt exclusion. You just melt the solid. If think about, just look around for a high throughput approach. What I mean by high throughput approach here, I'm going to elaborate a little bit more, is you have from initial experiment to all the way to analytical, there's no bottleneck. Certain technique, you might have a quick way to do something in a part of the process, but if you have to do the analytical individually, and so if there's a bottleneck, and then it's not truly identified as a high throughput approach. And in this, so this is from Symix technology, which is Freestate predecessor. Well, we in 2003 they published this, and and we still use the technology today within our group to do a high throughput screening cell screening, polymorph screening, single component, or even co-crystal screening now. And there's in this paper, it's Helming Tang from Amgen study using CIMIC Freestate equipment to actually do the high throughput sonic blending, which is also truly high throughput research as well. This is published in 2013. So how about applying Freestate technologies to automated solid grinding or solid drop grinding? They're very similar technique as well. That's definitely a reasonable question to ask. So let's talk about quickly about traditional solid grinding, solid drop grinding approach. So it's inherently a greener approach because you don't really use too much of a solvent at all. And most of the solvent you use might incorporate into the structure anyway. So it's definitely more greener approach than solvent-based approach. So currently the method is truly manual, which is you can do manual mortar and pestle grinding. It's truly just you grind it. That's actually the test case we did. And there are definitely more mechanical milling with the steel balls. It is pretty. I think you can set up multiple wells as well. I haven't seen it personally, but the potential problem with this approach is the milling part is very efficient, is very great, but the compound loading and the analytical part are not fully automated yet. So you definitely have a part you have to do it manually. So solvent drop grinding techniques, which when you compare with the solid grinding, which they're both viable techniques people use. So for solvent drop grinding techniques, it's only, just by the sound of it, it makes sense already. It's you're grinding this co-crystal with a small amount of solvent. And a lot of people are more prefer this technique is because they get more results from it, and it's very helpful. The solvent most likely help with the grinding itself, and also it might incorporate into the structure, like forming a solvent. So there's definitely a potential for automated high-throughput approach to this if we can replace labor-intensive and the time and material-consuming steps with automation at a small scale. And if that is achievable, and then we can start thinking, apply a lot of things we do within high throughput in other areas like polymorph study, reaction screening, solubility. You can start thinking about how to systematically and rationally approach something, like what kind of grinding solvent. You can map out the grinding solvent, map out the potential coformers, and in a more systematic approach. But before, we need to see if this technique can be automated. So in this case, we have a test case here, and we collaborate with one of our partners. So this is a manual grinding technique data from the partner. This structure, this diacid and pyridine is known. It's listed in the paper as well. As you can see, the bottom. Let's see. The bottom two structures, the XRD is of the coformers itself, and through manual grinding, you see you're going up, and what you do see is slowly the peak by the coformer itself start disappearing, and the co-crystal co-crystal peaks start showing up. So there's 4 to 5 main peaks that it consists of the co-crystal peaks. And disappearing, there are definitely a couple of big disappearing peaks from individual coformers. And the grinding cycle, definitely you see this gradual shift from an individual component to the co-crystal. So that's what we got in terms of our manual approach. Now, we have to come up with some variables in terms of how do we screen, how do we test our idea out to do automated approach. The equipment we have is through years of CIMIX Freestate development, and and at least that's what the equipment we have so far. We will see if we can adopt that, what we have in terms of using this and utilize for solvent drop grinding. So, and then here in this particular slide, I'm going to show you the variables we thought might be important in terms of getting the result we want. So this is just a guess at the time. So the first thing is a 1-to-1 molar ratio of the two components. And we think the amount of loading is definitely important. Because of the high throughput, you will see later on the loading amount is definitely important, because at the end all the material will be deposited on one glass plate. So you really do not want to have too much, because they might interfere with it, and you might want to don't have too little, and then you might have an issue with XRD quality. So the amount of material is definitely important, and also maybe if you have too much material, you have a hard time mixing all the components together. So the two variables we pick for this particular material loading, in terms of material loading, is 10 meg and 20 meg total. So, and within it is a 1-to-1 molar ratio of two components. And another thing we did that is, so the grinding part is we just get steel balls for grinding, and then we think maybe the amount of steel balls we need and the size of it might have an impact. So in this case, we have, so what we pick is the smaller size ones, 2.4 millimeter, and then we put 2 and put 3 for, that's 2 versus 3 for the small size, and the medium size we put 1 versus 2. So this is we'll see if that will make a difference in terms of co-crystal being generated. And also, in this case, the grinding solvent is methanol, and the amount of solvent, grinding solvent needed, and this is the final variables we want to test. So we use 10 microliter versus 20 microliter of methanol. So here is a little library. Typically, if we do full plate scale experiment screening, we do 8x12, 96 well condition. But in this case, it's a test case. This is the interaction between all these variables, and every variable will see the other possibilities. So if you see the design here, you have methanol on the column side, and then within there's a total loading of 10 meg versus 20 meg, and the steel ball size and the amount is also listed here. So all the variables are represented. And also, but there's a general condition for everything, because we're all going to put this in called in the one plate. So the general condition is what we decided to do is 900 RPM room temperature vortex it with the steel ball inside. This is just a grinding in the most, people understand that's grinding when you just kind of vortex the steel ball inside. So the planning stage, so now we got all these variables decided, and then now we need to go with the planning. So from idea to Freestate library studio design here, so this is in general, so you plan from this idea of this little plate, and now we're going to introduce that to our software called Library Studio Design, which then we can implement it later. And then later on, the Automation Studio, during the execution, will drive our equipment called Core Module 3. And another equipment, this is on-deck equipment we use, is called Crystallizer block. So in terms of overall workflow here, well, I'm going to go through with each step individually, but here is the overview of all the workflow we did. So we have to dispense the 2 co-crystal formers, and we're going to add the steel balls, and then we're going to add the solvent, grinding solvent, and then we'll do the grinding, and then we have to prepare for the analyticals, and then we actually acquire the XRD in this case, and then we do the data analysis. So so let's go from go to planning first. So here is the idea of we generated earlier, and then we're going to go through so this is a design we come up with. We just put in the middle of our 8x12 regular plate. And if I go to details about what the library studio looks like, is here you put in materials and parameters in terms of how much time, all the different things. And here is all the experimental step we're going to do, and in terms of adding powder, adding solvent, and doing the vortexing as well. And from the library design, eventually when we're ready to do it, we're going to introduce that to the core module that is controlled by Automation Studio. And the core module 3, here this is our our main equipment here. So there's a lot of variable unit operation that is configurable, that is listed on the right. And within the operation that we need for this particular study, we need the liquid and solid handling, we need vortexing, and we need to balance the way the compound out. And also this is the on-deck unit. Actually, the experiment is run within this thing called Crystallizer block. So if you take a look at the structure here, the build of this, you have a glass plate that is, you see, I think it would be easier. So you can either use a glass or quartz plate, where eventually the material will be deposited on this glass plate for the analytical at the end. And then you have this inserts where all this within this tubes, that's where the steel balls, the compound will be deposited into, and you have a gasket at the end to when you put it together. You put it together here. So after you close everything with the glass plates at the bottom and the gasket separate each well from each other, so that you build a pretty much a 96 well plate. So now, after we get all the equipment and individual block ready, so we're going to do our experiment. So the first thing we want to do is the solid dispense. So in this case, we want to add, so this is a dispense map for both 2 coformers. So here you can, this is a balance on our CM3 deck, and you have the crystallizer block within, you put it within the balance. After you put it in there, and then you can doing the dispense. And in this particular case, we use hopper. And the hopper, you can see this is where you can pick out from the deck that contains the coformer, individual coformers, and then to be dispensed onto this. You have to close the shields for the balance. So, and the second step, which is only a manual step at this point, is the addition of steel balls, which, because we have never done this type of thing before, we don't have equipment ready. But I just want to prove to you that it's definitely doable in terms of automate this step somewhat. So we do have a loader for stir bars, which we do use every day for a variety of different kind of experiment, from solubility study to reaction screening. So in this case, you have this stir bar loader, and you pretty much dump the stir bar into this, and then all the stir bars will trap into the little slot in here, but the trap door at there is still closed, and the rest of it you just kind of dump it out out. And so you have stir bar. So you have put the stir bar loader on top of the crystallizer block, which is at the bottom. It sits perfectly. And with the push of a button here, and the trap door will open, and the stir bar will drop simultaneously. So it's a very quick way to load all 96 stir bars into each individual vials. If this technology, so in terms of loading steel balls, we can definitely utilize this technology to do steel ball loading as well. So the grinding solvent addition, that's a liquid handling. That's we do very well here. And so this is, as you can see here, is after the powder dispense, after the steel ball has been loaded, we have sealed the plate, and now we can just add different solvent into it from the on-deck source. So now the grinding, I don't really have a video for this, but it's a still on-deck unit, but it's just vortexing it. You can buy off the shelf if you want to. It's just a vortexer, and you vortex for 900 RPM for 1 hour at room temperature. So, so after it's done, sorry. So the steel ball will be removed. We can use this steel ball retriever, which we do have. So you can all take out all the steel balls at the same time. And then you open up the crystallizer block for the final analysis. As you can see here, is the solid can be deposited after drying. So now we move the plate, which you can see here. As you can imagine, all these pictures are not from the study itself, and the plate on it is a different plate, but the idea is absolutely the same. You pretty much put the plate on top of this Broker XRD, and you have the camera. There's a camera on top that will eventually map each. So the step here is twofold. So all the plate, all the solid on the plate will be mapped, so the operator can see each individual wells on the plate, and then depends on where the solid is, because the solid can be deposited in a ring form or completely cover the whole well, or could be at the center. So you really don't know for each individual well where the solid is. So you cannot really just say scan the center of each well. So that means you're going to miss most of the solid that's been formed. So the protocol here is for each individual well that have solid that is worth XRD analysis, you will map it first to make sure with the camera, so you can see where the solid is. You mark that spot at the center, and then the XRD will come back. After you map it and you say go, XRD will come back to each individual position and scan it with the oscillating oscillating stage. And all the data will be saved to the database for analysis. So in terms of XRD analysis, so we, from the very beginning, you introduce the whole design idea into the Library Studio, and then you have experimental data from the CM3, and then you have the data, in this case, from Broker XRD. All this will be saved under a library ID. In this case, the library ID is 102905. So from the idea all the way to the implementation analytical save under same library ID for later analysis, ease of later analysis. So in terms of data analysis, in this case, we use Spectral Studio, where you can compare, you can see all the XRDs, you can overlay them, and you can do some simple calculation with the aid of the computer, the software to sort them quickly. So here's a visual kind of illustration of from idea to design to analytical. You can see from idea here to the design library design, and then to the final all the XRD we get from the broker instrument. So in this case, you can see here not only we have the column 6 and 7, that's part of the design, and also you have XRDs from the original co-crystal formers. We actually put in the same library for comparison overlaying purpose. Here, if you take a look at the data, so now we get to the data analysis part of it. So instead of overlaying all the spectrum together, which can be pretty confusing, so I'm going to kind of individually compare them, depends on the variables. So in this case, we do 10 mg versus 20 mg loading, and the 10 microliter versus 20 microliter grinding solvent comparison. So in this case, only the steel balls is all 3 small size steel balls. So as you can see here, the D6 is highlighted, and so what we're looking for is the peak that need to be disappear from individual component, how complete that peak went away. As you can see here, the D6 has peaks. Here is I don't like this color. Yeah, there's very little of that peak left. Everything else, there's still plenty of that peak staying there. So what's D6 compared to the rest of it? So less material loading, 10 mg versus 20 mg, and the more grinding solvent. In this case, 20 microliter with methanol. So now we know that condition is good. So let's compare. So we only compare the column of 10 mg loading, total loading. So everything else that is variable. So the fixed is methanol, 20 microliters of methanol, 20 microliters of methanol grinding solvent, and the total loading of 10 mg. So we're comparing that 4 conditions now. As you can see here, H6 is highlighted. As you can see, compared to the rest, all these 4 conditions, H6 has the best in terms of disappearing peaks. You don't really see these peaks, or very little of it. Even better than the D6 that is from a different column which has 3 small steel balls. In this case, the more steel balls and the larger size that lead to complete co-crystal formation. So here is to compare H6 with the starting both two starting materials. And as you can see here, is they have definitely completely different looks, and they completely form the co-crystal that is that resides in H6. So if you take a look at this, we have 10 mg of total loading, 20 microliters of methanol using 2 medium-sized balls. That leads to excellent conversion. So here, let's summarize today's talk. So the test successful because we use existing Freestate technologies that we can automate the solvent drop grinding co-crystal screening technology. And we clearly, from all the variables when we set it up, we're not sure either they're all going to work perfectly or they all might not work that well. But it is very surprising to us that we clearly differentiate the result differentiate which variables will give you better results, which we did not expect. So we clearly distinguish different variables' impact on co-crystal formation, which is we're very happy to see. And so this is the best condition. Vortexing at 900 RPM with two medium steel balls with 20 microliters of grinding solvent and 10 mg of materials for 1 hour at room temperature lead to good co-crystal formation, at least for this case. And test is continuing in terms of fine-tuning this technique and the workflow itself. And we actually, in fact, we move on to full plate screening involving novel APIs and like what I said earlier, a broad spectrum of coformers and grinding solvents that now you can start thinking about more scientifically how to approach this co-crystal formation with a full 96 well 8x12 plate. So with that additional screening, we actually have gain additional insight in terms of finding out this either the API itself forming co-crystals or the technique itself. So here, this is we incorporate the high throughput approach to crystal engineering of co-crystals. It's definitely possible to replace labor-intensive and the time material-consuming step with automation at small scale. And then small scale, in this particular case, did replicate what we saw with the manual technique. So if this is we can continue with this. We can enable scientists to systematically examine a broad spectrum of experimental variables. And so as you can see here is we do have a solvent-based approach that have been developed for a while. So now this is just a nice addition to that approach for co-crystal screening. So that will conclude my talk. And you can definitely check our website and email me. And now we can go to question and answer.
Thanks, Pooh. That was a great webinar. I really enjoyed it. Looks like there's a lot of really great work going on in your lab. We have had 3 questions submitted at this time, so I think we'll go ahead and see if we can address them all in this call, if that's okay with you. First question I have is, what's the grinding solvent's impact on co-crystal formation?
So like what I said earlier, so the grinding solvent that what way it does is facilitate the grinding, and then people actually definitely see better results a lot of times with addition of grinding solvent. I think that has some to do with the the solubility that dissolve either one or two coformers somewhat, and then they help the incorporation to form the cocrystals. And also, like what I said, and especially the paper I showed earlier, that the grinding solvent definitely have the chance to form solvates as well. So the grinding solvent can definitely have the chance to be part of the cocrystal. So grinding solvent and the identity of grinding solvent is definitely important. And especially with this technique now, you can actually survey a spectrum of different grinding solvent to see its impact on the cocrystal formation.
Interesting. And then would you be kind enough to elaborate more for the audience on any additional insight for fine-tuning the techniques that you've mentioned at the end of this presentation?
So one thing later on we a lot of so for the solvent-based technique, what we do use is especially, for example, for evaporation. A lot of time when the solid is deposited on the glass plate itself, we tend, after you open it, and we tend not to want to disturb the crystals because it can have formed single crystals. It can form something that is pretty fragile. So we pretty much want to do not. So that's one good thing about this automated approach. So when the crystal is formed, you don't really need to touch it. And for solvent-based approach, but in this case, and because one step we do need is to remove the steel balls afterwards. So the structure of the solid deposit on the plate might be kind of pull up, right? You can imagine you instead of a flat surface, you might have a little bit of a height or a 3D structure. So what we think is helpful is afterwards, after steel ball get removed, you can tap down the solid by using the same steel ball retriever that has a flat bottom. You just tap down all the wells to make sure the surface is flat before the XRD analysis. Also because in this case, the technique by itself is grinding technique. So by definition, you don't really form a single co-crystal. So you don't really need to worry about destroying something that is nice and nice good crystals. And but we do see it is helpful to pat down the grinded solid at the end. In terms of the study we've done, other study, the grinding solvent, polar versus non-polar solvent, definitely have an impact in terms of forming co-crystal with APIs. That's for sure. So definitely the need to introducing different grinding solvent is necessary.
And do you suggest using less volatile solvents?
So that's I think it's just imagine the whole plate is sealed, and because of the yes, so we're not talking about using. I at least we didn't use any kind of solvent like NMPs or DMSOs. It's all within reason, like heptane from nonpolar to THF to methanol to acetate to toluene. So things that pretty much one step I think I just mentioned briefly is after the solid the steel ball is removed, we're going to leave the whole plate before air dry. So pretty much the solvent will, first of all, most of the solvent might have got incorporated into the solvent, incorporated into the co-crystal, and if there are any, all will be gone by the time we're doing the analysis anyway. So just regular solvent, that's what I would say is a good starting point in terms of selecting grinding solvent, not the harsh, very high boiling solvents.
Okay. And do you have a sense of what temperature you reach during grinding?
We don't know that. So the whole thing is okay. That's a good question. And so in this particular case, it's vortexing on vortexer and with no temperature control here. So we really don't know. I can't imagine to be that high, but it's I would say maybe somewhat. Okay, I can give an example comparison between the mechanical milling that I see on the web and which very much more forceful in terms of grinding. I will say that kind of grinding, and they're talking about the shear power and the how powerful that grinding take place. I will say it's definitely milder in terms of grinding. And so the initial worry is this particular technique is not good enough. It's not, you're not grinded enough. You're not grinding enough for the formation. We're happy to see because we kind of know compared to this vortexing with steel ball inside versus mechanical grinding that is existence, that is definitely more powerful. I will say reach higher temperature than what we have here. But we're happy to see with this technique here, we still do form co-crystals.
Okay. And how do you manage dispensing the co-crystal formers? Do you use smaller hoppers or do you use manual dispensing?
Smaller hoppers will do. I mean, we in this case, I think Freestate equipment can easily handle 5 mix, and just imagine it really depends on the design. And in a real design, what you have is one API that will be dispensed into all wells. That's one dispense, and the rest of the coformers depends on how many you have, and then you can dispense that individually. And then you might use this maybe for a different talk, but you can use SV vial for that as for the smaller amount.
Okay. And the co-crystal formers that you showed in your XRD patents, were they ground under the same conditions? And can the starting material change form or solvate during grinding?
Can you repeat the question? Sorry.
So 2 parts. Can the starting material change form or solvate during grinding? That's really one question.
Okay. So the question is, so this I would say is a nice problem to have. Is you really don't know what you get, right? So you have your API, you have your coformer, you have your grinding solvent. So what can happen? Nothing can happen is one possibility. API form solvate with the grinding solvent, that's one possibility. API form coformer co-crystal, that's a possibility. API coformer with a solvate forming co-crystal solvate is a possibility. Coformer form with a grinding solvent form a solvate, that's a possibility. So we cannot really say, we don't really know what is going to happen, right? That's the power of high throughput is that you don't really assume too much. And because when you have this kind of a very systematic study and you have all these variables encountering each other, it's really hard to predict. And you don't really want to predict too much anyway at the beginning because assumptions tend not to really turn out well anyway. And so pretty much you have this approach. You have how many coformers, what the ratios, what the grinding solvents are, and then you do your experiment. So the best way, the reason a lot of time what we want to do is to do a full factorial design. What that means is every variables, for example, if you do 8 by 12, so you just do 8 grinding solvent, 12 coformers. And that's every variables see each other. And when you do that, and then you have all the XRD ready now, and you can compare different variables, how the similar regions in terms of XRD, for example, in this case, that's your analytical tool. Then you can start understanding if there are similar. So, for example, one coformers with different solvents, grinding solvent, give you a similar XRD spectrum, then you start getting a good sense of this might be forming co-crystal by itself without impact of the solvents. A lot of times, like there's another thing I want to mention is sometimes like a nonpolar solvent like heptane, that's rarely will incorporate. Then you see the co-crystal itself, and then you see more polar solvent like methanol or toluene, THF, that you see that you get a sense that's different from the heptane. Then you get a sense that maybe the solvent is starting incorporating into the structure as well. So the idea here is, on top of that, there's most of the time you have to think there might be incomplete formations, right? You cannot really say everything is formed complete or nothing happened. So a lot of times the reality is you see mixtures. So that's why if you have a full complete plate and with all the data in front of you and you overlay and compare them, you have a much better idea what's happening. If you just do one, sometimes it can be very confusing because all this possibility can happen because it's hard to predict at the time. I think I answered that question long enough.
I think it was a wonderful answer, Pooh. Thank you very much. We have time for a couple more, so I'll keep going. Do you ever see evaporation of solvent from well number 1 by the time you're doing your dispensing in well number 96?
Oh, so this is definitely we definitely solved that problem, because that will be a problem for a variety of different studies, not just for this one. So after you load the 2 coformers plus the steel balls, the plate itself is sealed. So you do have a puncture hole when you. First of all, it's not an open system. So if you have an open system, obviously the solvent you're going to have problem keeping. But it is a sealed system. We do this solubility study all the time. So in the solubility study, you put your API, you put your solvent. But you have 96 different wells, different solvent mixtures, and the seal is perfect. You never really need to worry about the first solvent being dispensed and the last solvent being dispensed. To be, you don't have to worry about the first solvent being dispensed. It is still pretty good.
Great.
So no worry. The answer is no worry.
The answer is no worries. Splendid. There's a question come in. Can you provide more detail about the grinding process? For example, mill and geometry.
I do give pretty much. So what the size of the steel balls? Is that what the question is?
I think this is just referring to the pitch between the wells and the ball size.
So I don't really know on top of my head the diameter of the. Let me show you like what I see here. I think the question is about the size of the. So we're talking about the height of this tube and the diameter of the well that is formed, which I don't really have that on top of my head. But the idea at the time when we select the 2 different steel balls is to obviously fit into the hole, but obviously not big enough to just kind of jam in there. You do have some room to wiggle. And but the ball size I gave it to you already. We just ordered that from, it's just simple steel balls. It's not something special. And the size of that well, I have to, in terms of dimension, I have to get back to you.
I think it's roughly a 9 millimeter pitch center to center, is it not?
Could be.
Yeah. Okay. So I assume that the tubes and the gaskets that you've got circled right now are disposable, or can you reuse them?
We do reuse them, and I think Freestate one, it is a consumable product, so it's not like we can reuse them forever. But we can definitely reuse them. We do wash them and reuse them at least 3 or 4 times before we discard them.
Okay, great. I have a clarification on the question that was asked regarding the milling technique. The question is the milling by vortexing, and can you remind us what the RPM you used was? It's
definitely milling by vortexing. So you have. I should maybe have show a video of the vortexing itself, but sometimes the video showing can be a problem. So let's see. I'm gonna. So pretty much after it's sealed, and you can see here it's sealed, and where's the solvent evaporation, you really don't have to worry about. There are two. Not only do you have this, sorry to answer earlier question, you have this rubber gasket, and then you have, in this case, a PFA sheet, or sometimes you can use Teflon sheet, and you seal the solvent, the whole component inside. But the is definitely the ball is 2 balls, medium-sized ball inside vortexing. By vortexing, the milling takes place, and the RPM we use is 900 RPM.
Great. And final question: have you conducted many screens on more complex systems, for example, larger molecules?
No. So the study we have done for real is still small molecule. It's still within small molecule realm. It's not a large molecule. But I don't know what do you mean by complex, but it's small molecule. It's a small molecule with variables. In this case, it's a 8 grinding solvent, 12 coformers. That is pretty focused. Is through calculation, and and then we, based on that calculation, we picked the 12 coformers are picked.
Okay. So by complex, the question meant pharmaceutical molecules.
Absolutely.
Okay. In the interest of time, I think we're going to wrap it up there. Thank you so much for all the questions. I know at the start I said only 3, but they were rolling in. So thanks for your attention, everyone. Everything that's left in the queue to be answered will be addressed. Rest assured, we will address them privately, and we will send that information out to you. So before concluding today's webinar, I'd like to invite you to visit our website to see previously recorded webinars on the application of Freeslate's high throughput research solution. These webinars are located in the technical resources section of the upper navigation menu and can be found under Learning Center. That's highlighted in this slide. So once again, this concludes today's webinar. And on behalf of Pooh and myself, I really want to thank you all for attending, and we look forward to seeing you at future events. Thank you very much, and have a great day.
Thank you.